Everyone, welcome to the last two sections for topic 10, 10.4, 10.5. We're going to talk about tangent lines and secant lines today. We briefly talked about tangent lines in an earlier section, so let's start with a quick review here. So the tangent lines are those line segments or lines that touch the circle at exactly one location. And we also had this other concept that if you have a tangent line that touches a circle, tangent line touches a circle, and then they eventually meet or intersect outside of the circle, that the two tangent segments were then congruent. So YB would be congruent to BZ, and then similarly, we could go all the way around this shape. So we could have this tangent line and this tangent line, both congruent to each other, and then we could also have this tangent line here and this tangent line here congruent to each other. So we're going to be able to use these tangent lines to solve for different parts of the circle, and then also we could find perimeters of shapes and so forth. So let's look here. If I was to try this, and I'm going to go through part A for you, and then I'll give you a couple seconds to do part B. We have some markings here. You can assume that all of these lines are tangent to the circle, meaning that they touch the circle in one location. So if this piece is 6 right here, that means that this piece must also be 6 right here. Well, they told you that this whole thing was 15. Well, 15 minus 6 means that this piece is 9. So then that means that this piece is also 9, because we know that this is going to be congruent here, and just the way that these were congruent. And we can keep going around the circle. We know, around the figure, which is, around the circle. We know this is 4, so that means this piece is going to be 4. 10 minus 4 makes this piece 6, which makes this piece also 6. So they asked us to find the perimeter. So the perimeter of this thing would just be the summation of all of those sides. So we can think of this side being 10, this side over here being 15, and then we can add the different pieces. This would be a total of 12, and then this side would be a total of 9 plus 4, which is 13. So our total perimeter here would be 50. Go ahead and pause and see what you can come up with for part B. If you approach part B the same way, we have a 6 here. You can start anywhere you want. That means this is a 6. We have an 8, which means this is also going to be an 8. If we take the 8 from the 11, we're left with 3 and 3. We have a 5, which means this is also 5. So our total perimeter for this one, we knew this side was 11. This side would be 5 plus 3, which is 8. This side here would be 5 plus 6, which is 11. And then this side here would be 6 plus 8, which is 14. So then our total perimeter here would be 44. So that was just a quick review of how we could use those tangent segments. We're going to keep talking about tangents and secants. There's a couple of formulas you're going to need to know for today, but just remember you can always write them down and refer to your notes whenever you're doing your homework or a quiz over this content. All right, so one of the first ideas is if we have secants and tangents that are intersecting inside or outside of the circle. So at this particular point, if you look at the diagram, we have, this is a line going through the circle and touching it at 2 points. So this would be our secant. So if you remember back to that vocab, secant lines touch a circle 2 points. Then we have this other line out here that is extending and touching the circle at only one location. This would be our tangent. So anytime you have this relationship where you have a secant and a tangent intersecting, there is a relationship between the arc measure and the angle measures. So if we look here, angle 2 and angle 1 are created along that tangent line. So angle 2 and angle 1, because they are next to each other on a line, we know that they would be supplementary. So that's one big idea here. Measure of angle 1 plus the measure of angle 2 would be 180. Now here's the other relationship. Angle 2 is this guy, and angle 2 has a relationship to this arc. And the relationship is that the arc is double the measure of the angle, or the angle is half of the arc. So if you look here, the measure of angle 2 is half of this arc ACB. And then it works similarly for angle 1. Angle 1 is this guy right here, and it is half of this arc. So the arc created by the secant and the tangent, or from B to A, is double the measure of that angle in there. And then similarly, it happened for angle 2. So let's look down here at these examples. So number 1 says find the value of x and y. Well, I can look at either one. We can find either one in whatever order you want. It doesn't matter. Let's go ahead and look at x first. So x is this angle created by this secant and this part of the tangent line. And x is going to be half of this arc. So we know that x is going to be equal to the 148 divided by 2. And if you cut that in half, you get 74 degrees. Now there's two ways you can find y. The simplest way, I think, is to think about the relationship that we had up here with angle 1 and angle 2. That would mean that angle x plus angle y should be supplementary because they make a linear pair. So that means that y, sorry, my stylus is having a minute, would be 180 minus the 74, which would be 106. The other way to find y is to think about the circle as a whole. And I'm just going to show you this so that you have this tool in your toolbox. But we know that y is this angle, and it should be half of this arc, RSP. So if I wanted to find the measure of arc RSP, I know that it's part of a whole circle, and then this 148 degrees was the other part. So if I took 360 degrees minus the 148, I'm going to get the measure of arc RSP, which would then be 216. And then I could say that y would be equal to 216 divided by 2, which means that y is 106 degrees. Either way is fine. These are both the same. Just so you have that tool in your toolbox, you can use that. All right, so let's look at the second one over here. It says that we're going to find the measure of arc DEF. Well, let's find DEF first. This is arc DEF. We notice that this is arc DEF, that it's going to be double whatever this angle would be. Okay, so you could do this one of two ways. We could say, all right, well, we know 64 has to be a linear pair with this angle right here. We could find that angle, double it to get the arc. Or we could take this angle, double it to get this arc, and then subtract that from 360. It does not matter to me what method you pick. I'm going to go ahead and just say, well, 180 minus the 64, if I subtract those two, okay, you should get 116. So that 116 is this angle right here. So then that means that the measure of arc DEF should be 2 times that 116. And if you do that, you get 232. The other way then obviously would be doubles the 64 to get this arc, and then you could subtract that from 360. But either way is sufficient. So this is the relationship when you have a secant and a tangent intersecting with each other and they're touching at that one point, which would be the point of tangency. There's another method, and this is a different way that secants and tangents can intersect. So if you look back here just for a quick moment, we had an intersection point that was lying on the circle. Now we're going to move to an intersection point that is outside of the circle. So we're going to have an intersection point outside of the circle, regardless of if it's, these would be two secants intersecting here. This would be one secant and one tangent line intersecting here outside the circle. And this would be two tangents intersecting outside the circle. But there's a formula. No matter what you have, if the intersection is occurring outside of the circle, this angle, the point of intersection, is equal to the difference of the intercepted arcs and then divided by 2. So if we look at this first example right here, all right, the outside angle is what we're going to try to find. The outside angle is this guy right here, angle 1. Okay, so if we look where the secants go through the circle, then we create this arc and this arc. Since we're doing the difference, we're always going to do big arc minus small arc. In this case, it would be x minus y, and then we would divide it by 2. Just like that, or multiply by 1/2. For the second example, we have our angle out here, and the intercepted arcs would be this piece and this piece. Same thing, big arc minus small arc divided by 2 gives us this angle. Third example, angle outside the circle, right here, and the intercepted arcs are this piece and now this piece. So x minus y divided by 2 gives us that angle. We actually did something like this in our last section, 10.3, where the intersection was inside the circle, and we did arc plus arc divided by 2. So if this was x and this was y, this angle here was x plus y divided by 2. So here's how you can separate these two. If the intersection is inside the circle, you're going to add the arcs, divide by 2. If the intersection is outside the circle, like these, you're going to subtract the arcs, big minus small, and then divide by 2. Just to keep it straight. I know it kind of blurs together with all these different theorems and formulas. So let's go ahead and try. I'm going to do this first example, and then you're going to try the next. So up here it says, what is the measure of angle HLK? Well, angle HLK is this guy. This diagram's kind of tight, but that's okay. So this angle should be the difference of the intercepted arcs. So it'd be this arc and then this arc. Let's get some color in here so you can see the differences. So we have this arc here, which is 102. We have the other intercepted arc, which is this arc here, which we need to find. And then we're going to solve for this angle. Well, we know this is 102. And basically, if these are tangent points, then that means that arc HJK, the measure of arc HJK, which is this guy, should be the difference of 360 and 102. So if you take the difference of 360 and 102, you get 258. All right, so now that we found that, now we can go ahead and find the measure of angle HLK. So the measure of the angle is just going to be big arc minus small arc divided by 2. So the measure of angle HLK would be 258 minus the 102, big arc minus small arc, all divided by 2. If you go ahead and put that into your calculator, you end up with 78 degrees. All right, so using this idea, big arc minus small arc, all divided by 2, go ahead and see if you can try the 2 examples here. Pause your video. Okay, so when attacking this first one, the measure of angle XYZ, which is this guy right here, is 68. We're trying to find the measure of arc XZ, which is this guy, and we know that this other intercepted arc right here is 224. So remember, we're going to do big arc minus small arc over 2 equals the angle. This time we're given the angle, so that's what we're going to set it equal to. So we would do 224 minus, let's go ahead and call, we'll just use the arc, all over 2 equals 68, because this time we're given the angle. We want to get rid of this divided by 2 by multiplying by 2. So if I multiply by 2 on both sides, my 2 is going to cancel on the left-hand side, and I'll have 224 minus arc XC equals the product of 2 and 68, which gives you 136. Now, once we have this, some people like to combine this all in one step. Some people like to make this 2 steps. I need this arc to be positive. So if I add it over to this side, and then I subtract my 136 to the other side, I'm going to be left with 224 minus the 136 is 88 degrees, and that's going to equal the measure of my arc XZ. So that would be this guy right here. So remember, big arc minus small arc equals the angle. Over here, we're going to do a little bit more work, okay, just because it's a little bit more algebra heavy, but the approach is still the same. Big arc minus small arc over 2 gives you this angle. So the angle is what we're going to be setting this equal to. I'm going to extend my page here. So this would be my big arc. This would be my small arc. That's 30 degrees is my angle. So 5x plus 10 minus this whole thing here, 3x plus 4 all over 2 equals 30 degrees. Now a lot of us will make a little mistake here because we'll forget to distribute this negative. So really, this would be 5x plus 10 minus 3x minus 4 all over 2 equals 30. Now we can keep going the same way we did over here. We can multiply by 2 on both sides. I'm going to go ahead and multiply by 2 and combine my terms. So 5x minus 3x gives me 2x. 10 minus 4 gives me 6. And if I multiply that 2, I'm going to get 60. If I subtract my 6, I get 2x equals 54. And then if I divide by 2, I get x equals 27. So that would be the way you can still manipulate these problems with a little bit more algebra. Okay, we're moving towards the last couple of ideas here. Remember, all of these ideas were how to find angle measures with secants and tangents. So if we go back, we have all of these different properties, big arc minus small arc divided by 2, and then we had the idea here of the arc being double the measure of the angle. That's all angle measurement properties. Now we're going to move to side length properties with secants and tangents. So the first idea is when we have 2 secants that are intersecting, we can still find measurements of their segments. Now you can look at it as like length times length. I like to think about it like this. Whole secant multiplied by the outside piece. So I'm going to write whole secant multiplied by outside secant equals, and that same relationship exists with the other one. So we can do whole secant multiplied by this outside piece. Now this formula or this process gives us the length of secant segments. Now you might be thinking this is kind of pointless. Why do I need to know this? This has a lot to do with architectural structures and that kind of stuff. So while it might seem, minuscule now, it actually is part of a bigger I guess, application to the real world. So let's look at this example. I'll do this one with you. So we have two secants. So I'm going to do whole secant. My whole secant would be 8 plus 4 times my outside piece, which would be 4. I'm going to set that equal to the other whole secant. Notice this is x plus 6, not 6x, times the outside piece, which is 6. And then algebra happens. 8 plus 4 is 12, and then 12 times 4, the left side, we're going to get 48. And then over here, you can either distribute or you can leave it as x plus 6 times 6. For this example, I'm going to go ahead and distribute. I'll show you how to leave it later. So this would be 6x plus 36. If we subtract our 36 over, we get 12 equals 6x, and then divide by 6, and you get x equals 2. So that would be a quick way to find this value here. Obviously, this would be not drawn to scale, or maybe not very closely drawn to scale, based on the other values that are in the diagram. Okay. So the last piece of, I guess, segment, tangent, intersection, and segment length, instead of angle measures, would be if we have a secant segment and a tangent segment intersect. So in this case, when we have a secant segment and a tangent segment, we kind of have like a Pythagorean theorem relationship. So basically, this is our tangent segment, touches the circle one time. This will be our secant segment, and we're still going to stick to that relationship of whole times the outside piece. So while you might see this formula, I like to teach the process instead, because you're not always going to have A's, B's, and C's. So basically, it's the tangent segment squared equals the whole secant times that outside piece. So just like before, whole secant times the outside piece, but this time, instead of setting it equal to that similar relationship, we're going to set it equal to the square of the tangent segment. So down here in this example, here's our tangent segment. So we're going to do 20 squared equals our whole secant, which would be 4x plus x, times the outside piece, which is x. So 20 squared, that's going to give us 400. 4x plus x is 5x, and then times x, this would be 5x squared. Now we would simply go ahead and divide by 5, so we'll get x squared equals 400 divided by 5, I believe is 80, yes. And then you would just simply take the square root, so x would be the square root of 80, you could leave it as a radical, or round it to about 8.9. Okay, so this would be about 8.9 here. And you could substitute it back in to get this value, and you could go from there. Okay, why don't you guys take a minute, copy these down, try these into your notebook. Go ahead and pause your video. So the goal when approaching these problems is to figure out what it is that you're actually looking for in your diagram. So my first question is, am I solving for an angle or a segment? In this case, I'm solving for segments because I don't have any angle measures. Then I have to ask myself, do I have secants intersecting, or secants and tangents, or some sort of combination? So in this case, I have a secant line because I have it going through the circle, touching it twice, and I only have one touching here, or one point of intersection here with this line, so this would be a tangent. So I'm going to use that idea of tangent squared equals whole secant times outside secant. So my tangent squared would be 20 squared. My whole secant would be 30 plus y, and then my outside secant would be y. So this would be 400 equals, I'm going to have to distribute here. This would be 30y plus y squared. This is getting a little tricky. So basically we can't simply divide just like we did last time and take the square root, but I can subtract this 400 over. So I could get y squared plus 30y minus 400 equals 0. And now I have a quadratic, and deep dark days of Algebra 2, you guys can now factor. If you remember your factoring skills, the idea is to think, all right, what factors of my C value will obviously multiply to give me the C value, but add to give me this B value. Well, this is a nice one. So we're going to break this down, y and y. Our sign here says we're going to have a plus and a minus. 400 is the same. You could do 20 times 20, but 20 and 20 don't give us 30. But we could do 40 and 10. 40 times 10 gives us 400, and we could do a positive 40 and a negative 10 to get a positive 30 as our B value. Now then we said each one of these pieces equal to 0. We know we can't have a negative y value. We can't have a negative length. So the idea of y equaling negative 40 is not going to work. So our solution here would be y equals a positive 10. A little bit extra, I know that one was. We'll stick to the more basic problems like the last example, but just a good practice problem for you. Okay, number 2. This time we're finding segment lengths again, and this time we don't have any tangents. We have a whole secant and its outside piece, and then we have another whole secant and its outside piece. So we're going to do that whole secant times outside piece equals whole secant times outside piece. So if we start with the top one, our whole secant would be x plus 18 times our outside piece of 18 equals our whole secant 24 plus 16 times our outside piece of 16. Now this one, I'm going to show you how to solve this without doing the distributive property on the left-hand side. So let's leave this left-hand side as x plus 18 times 18. Over here on the right-hand side, the 24 plus the 16 and then times 16 gives you 640. Now, if you didn't want to do the distributive property, you can simply divide this by 18, divide this side by 18. These are going to cancel. So you get x plus 18 equals 640 over 18. Now we can go ahead and just leave this as a fraction, and then we're going to end up subtracting the 18. So x would be 640 over 18 minus this 18. You could put all that into your calculator. Rounding to the nearest tenth, you get about 17.6. And if you didn't like this method, you can always just go ahead and distribute when you go up to this top part here. Either way is fine. All right, last problem is a little bit of a challenge. I want to see if you can kind of combine what we did previously and what we did today to solve for a couple missing segments. All right, so take a moment, copy this down, see if you can find the value of x and y. I'll give you a hint. It might be easier to find y first using the methods that we learned today. See what you can come up with. All right, so when you approach this problem, let's think, what do we have going on? Well, over here, I have a tangent line. Okay, so I have a tangent segment. Here, this is a secant segment. And then I also have going on inside of my circle, I have a chord with a chord. So we've got a lot of different things going on. We want to isolate a combination so that we have just one variable in the mix. So right now, we can think about our tangent secant combination. Our tangent secant combination would be the 15 and then this whole purple segment. We actually only have one variable there, which would work. You could also think about our chord combination from 10.3. Our chord combination would be the two green lines. The two green lines, we actually have an x and a y involved, so that's not going to help us. So we're going to go ahead and start with this tangent secant combination. And if you remember from what we did today, that would be tangent squared equals whole secant times the outside piece of the secant. All right, so our tangent squared. So we do 15 squared. The whole secant, now this whole secant is this whole purple line, would be 9 plus 7 plus y, and then the outside piece would just be this guy. When we're taking care of this problem, we can easily do the 15 squared and get 225. In here, 9 plus 7 gives me 16 plus y, and then times 9. I'm going to go ahead and divide by 9 on both sides instead of distributing. So 225 divided by 9 gives me 25. This would be 25 equals 16 plus y. Subtract your 16 over, and y equals 9. So now that y equals 9, now I can move to my chord-chord relationship. And remember that chord-chord relationship says that if we take the product of the pieces of the chords, so 4 times x, we can set it equal to the product of the other pieces of the chord, 9 times 7. So this would be 4x equals 63. And then if you divide by 4, you get x equals 15.75. All right, if you got that, great job. If you struggled, it's okay. That was a challenge problem. So let's go ahead. This is, like I said, the last part of this unit or this topic. So for tonight's homework, it's actually going to be just practice over this material and a little bit of material from 10.3. It's the attachment that is already in the assignment in Teams. Make sure you show all of your work on a separate sheet of paper. If you want to copy the diagrams down, that would be wise because you're going to have an assessment next week to work on, and it'll be easier to look at all of your stuff, picture and work, if it's in one place. But you'll upload your notes from today and your homework to this assignment, and have a great weekend. Have a productive day. Thank you.